All right. Thanks, Matthew. Hey, everybody. Yeah, so that's right. We're going to be talking about a pretty crazy production use case for Ray at Amazon today. This has been years in the making, so I'm excited to get up here and talk to you about it. There's some other people I see in the audience back here who have played a huge role in making this happen. I'm looking at Raghavendra sitting right back there. So there's people around here that have also played a big role in this. Definitely far from a one-person effort. Lots of teams collaborated across Amazon to make this happen. But yeah, I'm Patrick Ames. I'm from Amazon. I'm a principal engineer in the business intelligence organization at Amazon. And we are going to tell you about an exabyte-scale production migration that we did and is still ongoing from Apache Spark over to Ray. And this migration is pretty unique. We'll start with an overview of the kind of problem space that we're in, introduce you to it, and talk about this so-called compaction problem that we have with our data residing in our business intelligence data catalogs at Amazon. Why we decided to migrate this particular workload from Spark to Ray, even though this is fundamentally what we're going to be talking about as a big data processing workload. So you may look at it and say, well, why exactly did you choose Ray for it? We'll get into that as we go through the talk and talk about our results, which I've been very happy with so far, and future work that we're planning on doing in this space in open source and internally. And then we'll close up with ways for you to get involved and help out with the project yourselves going forward. So without further ado, getting into the introduction, let's start with talking about the journey from data lakes to lakehouses over the years. So those of you that are maybe involved in this space a little bit more, some of these terminologies that I put up here are familiar to you. I think back in the 2000s and 2010s, data warehousing was a very popular thing that we were all doing. And here on this slide, I'm kind of using it to refer to this historic method of using especially relational databases to run coupled storage and compute over structured data. And at Amazon, we were doing the same thing. We were running one of the largest Oracle data warehouses on the planet. And that's, I think, a kind of a direct Twitter quote from Werner Vogels on our side. Like, it was huge. It was, at the time, 50 petabytes of replicated Oracle data across all kinds of servers. And we eventually federated that into an S3-powered data lake, right? And so at the time, a lot of people were migrating away from this coupled storage and compute model into decoupled storage and compute. And that's where data lakes kind of come into play. Things like HDFS and S3 can really help you with that. But they don't bring a lot of structure to your workloads. When we start migrating these workloads into S3, into data lakes, you're starting to sacrifice things like ACID compliance, if that term rings a bell for any of you, atomicity, consistency, isolation, and durability, right? These things that make sure that it doesn't become a data swamp, as the terminology is sometimes applied to data lakes. You lose a lot of that when you go to data lakes, right? So how do you get it back? Well, that's where data cataloging starts to come into play. And Hive was one of the earliest things there to say, hey, we're going to use like partitions inside of directory paths and allow you to use your directory paths by itself just to bring some structure to your data, to group it into partitions and tables and stuff like that. And then Iceberg and Hoodie and Delta Lake and Nessie, these other projects have become more sophisticated with their metadata grouping, and they start to give you some of the primitives you need to get that ACID compliance back. They start to give you transactionality primitives and stuff like that. And then the lakehouse model came along, I think, in 2021 or so from Databricks, where basically you're saying, it doesn't have to be one or the other. You can have decoupled storage and compute and still have ACID compliance, but the two need to kind of cooperate with each other and get along. And it's been a very interesting journey, and where we're at more in the business intelligence space on Amazon's side is kind of more towards that lakehouse model, where we have decoupled storage and compute, but we still go for ACID compliance. And we're very focused on kind of spinning the business intelligence flywheel here at Amazon as kind of a centralized hub for data analytics and ML pipeline data I/O at Amazon. And this flywheel basically focuses on collecting business insights, making data-driven decisions from those insights, improving operational efficiency, and then that leads to collecting even more business insights. And at a certain level, it gets kind of meta. We're collecting business insights business intelligence insights about the business intelligence organization, right? And using those to improve our own efficiency as well. And then there's this kind of BI decision evolution and general decision evolution. It doesn't just apply to BI, where we're gradually migrating more away from just purely manual human-in-the-loop decisions to supervised decisions where maybe there's a little bit of ML involved in it, but somebody's kind of babysitting it and making sure it doesn't make any critical mistakes to the business. And eventually, we'd like to kind of get to this whole unsupervised decision realm, at least, for some subset of decisions. I don't think you're going to have like auto CEO anytime soon, but Ray is kind of helping us transition into more supervised and where it's safe, unsupervised decisions in these business intelligence pipelines. And a brief history of Amazon BI, I touched on some of this a little bit, but yeah, 2016 to 2018, we migrated this enormous 50 petabyte Oracle data warehouse to our S3-based data catalog. At the time, it was just kind of a data lake. It became a data catalog as we put on metadata and got organization around it. And then we started to kind of form these underpinnings of what we might call a lakehouse now, where we learned how to do schema and partition evolution, data repair and time travel operations, and then LSM-based change data capture, so log structure merge, change data capture, compaction, as we call it, applying inserts, updates, and deletes that are written to a table over time using Spark on EMR. Then we did some data pipelines as code, where we kind of built some applications that helped us take a multi-system pipeline consisting of Spark and Ray and Redshift and all these other applications and define them as a single logical application. 2019 to 2023, we started getting into Ray integration for data quality analysis, first off, which kind of helped us vet the stability and capabilities of Ray at Exabyte-Scale. And it also prepped us for the Spark to Ray compaction migration, which was a really critical workload. We're creating read-optimized versions of these tables. And everybody in their business intelligence pipelines are going to depend on this. So data quality analysis was going to help us get this over the bar by comparing Ray and Spark results. And it was also the first big use case where we vetted Ray at scale, like can Ray actually run data processing operations at Exabyte-Scale. And so a quick aside about why exactly we chose Ray here is, initially we weren't looking at it strictly for compaction. We were looking at an API that would help our data scientists and ML engineers scale their workloads on Python better. We found it, of course, it's Pythonic, it fit the bill there. We found it to have very intuitive APIs. Those of you that have worked with it, it's pretty much plain Python with remotes, dot remotes added in, and Ray remote annotations, stuff like that. And it was very scalable. That's what we were looking for, performant, efficient, and potentially unified. We saw a potential here that we could do more than just ML with it, that we could start to run large segments of our data processing pipelines end-to-end, potentially using a single distributed compute fabric. And if we get into our particular problem that we're solving here and talking about, it is this fundamental compaction efficiency problem. So we'll start out with a simple definition of efficiency. I think the oldest definitions of efficiency go back to physics, which just says, hey, it's useful energy output divided by energy input. Another general definition in computing, I'd say, well, it's useful computing output divided by the resources you input into it. So basically, the more work you can do with the same resources, the more efficient you are. So as a simple example, if you have two equivalent computers reading the same 2 gigabytes of data in 1 minute, if system A can do 2 gigabytes and system B can do 4 gigabytes a minute of input tabular data, we say system B is twice as efficient as system A, right? So pretty straightforward when we apply that to a very specific use case, all other variables being equal. And then let's back up a little bit. For those of you that are ML engineers, I'd like to give you a holistic view of your machine learning pipeline's efficiency. First off, I want you to know that, of course, you inherit any cost that your upstream data providers have. If you're just reading strictly from S3, you're going to get some of S3's costs to store your data handed back down to you. That's part of what goes into your bill, right? And then whatever costs you incur, if you're building a service, of course, you're going to pass those down to your downstream consumers as well. So this compaction use case that we're talking about is a very fundamental upstream use case for probably a lot of your machine learning pipelines, either implicitly or explicitly, from where you're sourcing your data, and would thus have an impact on the cost of your pipelines. So think about, for all your pipelines, where exactly your data sets come from, and at what cost and frequency do they arrive. And I think we'd all like it to be cheaper and quicker, right? Yeah, nobody ever argues about getting things cheaper and quicker. And that's fundamentally what we're after here. And that goes into understanding Amazon Business Intelligence pricing. We charge internal pricing to other Amazon internal customers to use business intelligence. So we basically have a set of administrative costs that we divide evenly amongst thousands of distinct data consumers, where everyone's charged the same normalized amount per byte that they read from our catalog. And our biggest administrative cost, arguably, is compaction, which does just take this input list of structured S3 files that just say, hey, these are records to insert, update, and or delete from this running table of change history, right? And the output is a set of S3 files with all inserts, updates, and deletes applied. It's a merge, fundamentally, right? We've merged it in and said, hey, I did it for you. Here's the final result. Here's what the table should look like. And why is it so expensive? Well, it runs after any right to actively read tables in our Exabyte-Scale data catalog so that all the reads coming at it can be optimized. It's producing a read-optimized view, fundamentally. And of course, this incurs a very large compute and storage cost. You're storing a lot of data and you're computing over a lot of data in perpetuity. And yeah, we're doing it so that reads can be optimized, because we do reads a lot more than writes for most of these tables, right? We do a bit of, at read time compaction as well, but the vast majority of our use cases and cost falls under the copy on write compaction model, right? If you're into Hoodie or Iceberg, you'll see the terms copy on write and merge on read thrown around. We do both. We're talking more about copy on write here in this presentation with compaction. And also we use it to enforce security and compliance policies like GDPR. We fundamentally rely on this to delete sensitive customer data so that it's not visible to any of our catalog consumers. So I'll give you a quick example here using our open source DeltaCat APIs, which is a Ray ecosystem project, which is currently experimental, but we are using it in production internally. We just haven't ported it completely to Iceberg and Hoodie and other catalogs yet. But if we give you an example here of like a sample S3 catalog you can initialize, let's say you have a production catalog here, and we just initialize it, saying DeltaCat initialize this catalog, and we give it an endpoint. Say that's where the catalog resides in S3. And then we load a pandas data frame into it. Pretty simple. Column 1 is 1, 2, 3. Column 2 is ABC. We're going to say create this table, store the content as Parquet, and then we are going to write another pandas data frame to this table after we created it. We said, hey, just append this pandas data frame that I gave you. And its content type is, again, Parquet. It's a simple insert of the two, so we should expect the two tables, the two pandas data frames that we inserted to be simply appended to one another. And if we look at under the hood how this whole thing happens and how the compaction problem comes into play for this very simple example, you started with this pandas data frame, one right there. We create a delta, which is a metadata layer, that's going to store references to your S3 files, right? We take the pandas data frame, we write a Parquet file to S3 for it. We reference that Parquet file inside the delta, right? And we append it as a delta onto the sample table, right? So this table in the metadata layer, in the data catalog metadata layer, you have two deltas, right? The first pandas data frame, the second pandas data frame. And then we're going to send an implicit compact operation. Hey, a new delta arrived. Let's do a copy on write compaction of it. That's going to launch another array cluster, which is going to read both of those deltas, the contents of the pandas data frames we saw earlier. It's going to create a new revision of the table. It's going to store the results later of compaction. And it's going to simply concatenate the two in this case. Pretty straightforward. And the concatenated result is going to go into a new delta. So this delta, the file that's going to go inside of it and be referenced inside of it by URI is written to S3. we reference it in the delta, we put the delta in the new compacted table, we commit the table. Once it's committed, other people can be like, okay, you're good to go. You can read the table now. You don't have to do that concatenation every time you read it yourself. Now, more interesting is a merge operation. And that's specifically what we're more focused on optimizing here. So say we inserted that same 124 DEF, second pandas data frame there. But we said, do a table write mode merge instead of just an append. Well, in that case, the end-to-end workflow changes to this. And the key part of it is the far right side where you're seeing the merged column 1 and column 2 there. Wherever column 1, if that was our merge key, wherever those values matched, it would be overwritten with the later delta's values in column 2. So you see 1 and 2 were updated to D and E from A and B. 3 and C was never updated, so it stays the same. 4, F was inserted, right? So this is fundamentally a deduplication problem. At its core, very large deduplication problem, finding matches, and then inserting things where matches don't exist, updating things where they do. So when we're looking at our Spark to Ray migration in this context, we're going to look at some key milestones, challenges, concessions we made, and lessons we learned. So laying out kind of a timeline here, back in 2019, we launched our initial Ray investigation and did benchmarking and analysis of could Ray be a good fit for this and any other arbitrary distributed compute problems that Amazon has. We thought, yeah, it could. And specifically, we think we could even make a much better compactor with Ray. So let's try it out. So in 2020, we came up with a design that we called the Flash compactor. And we made a proof of concept code implementation of it, ran it directly against S3 alongside Spark and said, oh, looks pretty good. Then we came up with the next step. If it looks good, how are you going to run it in production? Well, we needed some serverless job manager, which is a big problem in and of itself. So we came up with a Ray job management system design and implementation in 2021. And then 2022, we did Exabyte-Scale production data quality analysis, which we talked about earlier with Ray, to vet that everything was working correctly, job management works correctly, Ray can process exabytes of data. It all looks good, even in prod. And then we started shadowing Spark with a compactor. Okay, keep Spark on, start running Ray side by side, see how they actually do when they're both off to the races at the same starting point, and compare their results to each other using the data quality framework. And then we did production migration from Spark to the Flash compactor on Ray here in 2023. And there have been a lot of challenges along the way here that we've tried to tackle. One of the biggest challenges here is, of course, correctness and backwards compatibility with Spark. Correctness is an interesting thing because you could get in a lot of long debates about what exactly is correct results, even to a simple problem like deduplication. You get into type systems and differences between type systems, and they don't always agree about one value being equal to another. You know, even simple things like integers, some type systems have a concept of -0 and other type systems don't. And timestamps are particularly tricky. So basically we said, well, we want the end results of this produced by Ray to look as close to Spark as possible. And then your other problems are, okay, how do you actually make sure that they're backwards compatible with Spark, equivalent to whatever Spark is producing on a strict budget? Because you can't just, you know, you're processing exabytes of data. You're not going to also compare exhaustively exabytes of data without blowing up a huge budget. And then automating those workflows, right? And budgeting for deferred results is a big thing too, right? We're running them in shadow mode. Costs are going to go way up before they go down. So you have to have a budget that says, and buy-in from your business leaders to say, hey, do you want to spend a lot more money this year so that you can save money next year? That can be a hard proposition to push through unless you have really convincing data that says, I promise you, you'll save money. And here's by when you'll break even. And we also found out that, you know, what do we want to target? We found out the largest 1% of tables are about 50% of our cost. So we said, okay, we'll go after those first. A small number of tables, a lot of cost sunk there. But they're also hard to work with. And then operational sustainability was super hard. Cluster management is a hard issue by itself. Just infrastructure, the infrastructure we needed from EC2, we wanted more infrastructure than they had available at times, right? We were already sucking up a huge pool of EC2 instances in various regions for Spark compaction. Now we wanted even more to run Ray side by side. So we had to get into warm pooling discussions and all kinds of crazy stuff. And a separate team is fundamentally dedicated to the sole problem of cluster management at Amazon today and making sure clusters can launch reasonably fast and distributed across various availability zones. And they're heterogeneous clusters that consist of multiple instance types. We go fishing for the quickest instance type we can grab, basically, for the cheapest cost. And then, all the stuff that goes along with that's pretty hard. Reducing cluster startup times. Cluster management out-of-memory errors was a big problem, too, that we were facing. And regressive tables. Some of our tables consist of millions of tiny files, others a few huge files. There's a lot of challenges there. And some of the fundamental lessons we learned, some big ones, your customers ultimately define correctness. So don't waste your time too much getting into debates with each other about what is a correct result to a particular query. Ultimately, you can't break your customers, right? If your result is more correct, but if you have some customer on Redshift who needs to consume it, but Redshift then crashes because your more correct result with 100 points of decimal precision is more correct and they can't consume it, well, it doesn't matter. You need to listen to your customers and what they expect. And Murphy's Law, of course, that when you're dealing with things at Exabyte-Scale, if there's there's a 1 in a billion chance that that'll happen, it's going to happen many, many times a day, if that's like a per record chance. So you can't get away from fixing all your tiny little bugs. When choosing infrastructure, we found EC2 in general is what we turn to for running greater than 10 terabyte jobs. And if you're dealing with less than 10 terabytes for this type of workload, we'll turn to AWS Glue. Easier to run and better cost because you're spending less time spinning up a cluster. AWS Glue is going to spin up your cluster very, very, very quickly. There's next to no provisioning time for your cluster, unlike EC2, as we'll get into. And so some of the concessions made was we conceded to backwards compatibility, as we said. Specifically, that meant we did things like we regressed back to Parquet 1.0 from Parquet 2.0, from the latest 2.x Parquet version, so that we could be compatible with Spark. And over time, we found different tables present different challenges. So we started favoring this pattern that says, well, you might actually have multiple disparate implementations of something like compaction depending on what table it's going up against and depending on what hardware you can give it. There's not maybe one implementation to rule them all. But you have to now balance the ROI of maintaining those. And then we got more into manual memory management, right? Automated garbage collection is great as long as you don't care a whole lot about efficiency. The more you care about efficiency, the more you get into managing your own memory. It seems to be a universal law of computing almost. And that was certainly true in this case too. Okay, so some fun facts about the migration here. Some things that you might not have guessed going into this is all of our production code actually calls into Java APIs via Py4j. So anybody out there that thinks you can't use Py4j in production, well, it actually is possible. I don't know if it's advisable. Don't do it. Don't put in Python to Java shims if you don't have to. But if you have to, and we kind of had to because Amazon has such an enormous Java code base that we had to tie into under the hood, well, you can actually make it super stable if you work on it and you're careful about how you do it. And all the code we actually run in production is legitimately checked into open source. We don't have a secret fork or anything like that we run in production and then keep the open source stuff separate. So you can review it in open source. And we still have some work to do before it works for Iceberg, but we're trying to bring it to other catalogs as well. And so let's get into some of the results that we picked up here. This is kind of the interesting stuff. So some of our key production statistics here are, so our largest cluster sizes that we're running in production right now, the P99 is about 27,000 vCPUs per cluster, so pretty huge. P99 of data process per job is about 130 terabytes, and P99 of performance is about 763 terabytes per hour. And our efficiency for spot instance pricing, which is similar to the pricing we get internally with our kind of warm pooling and EC2 instance selection algorithm, is a mere about 12 cents a terabyte. Even if you do on demand, it's not too bad, about $2 a terabyte average. And keep in mind, like things like the sort record are about 97 cents per terabyte right now for cloud sort, which is actually also powered by Ray, that record, and the Exo Shuffle paper. And we run about 570,000 vCPUs of Array across all of our Array clusters every day, process about 1.5 petabytes a day, have over 300,000 consumer queries running against these jobs every day. And overall, we're reducing our cost versus Spark. At most, these are fully automated clusters that are just being provisioned without any hands-on intervention. We're still getting about 76% improvement on our P99, about 30% with our average improvement, focusing on the largest tables, moving from Spark to Ray. And another upside surprise is we were able to tune our algorithm to avoid unnecessary copies of S3 files versus Spark. So basically, we would group a compacted dataset file by the date each record was last updated, and then we would copy each S3 file that was untouched by the merge operation by reference instead of copying the file contents. And then we would repeat that initial grouping as basically the untouched file ratio degrades over time. And this put our cost reduction versus Spark, since we were initially focused on only reducing compute cost, this actually improved the cost above and beyond the cost of compute to about 114% of just the cost of compute. And this is assuming that you have a garbage collector in S3. It's worse if you don't. Our garbage collector maybe leaves old files sitting there for 2 days. So we're saying if it sits there for 2 days, that's the cost reduction we're getting. And some interesting graphs here to quickly review. There's a lot of insights. And one insight from the whole migration is, at scale, basically QA and telemetry in production become the same thing. You can't test every case, so your quality assurance is only as good as your metrics. And this shows the orange line there is an important one. When you're going left to right across this graph, you're going increasing cluster size from 1,000 vCPUs on the far left to about 27,000 CPUs on the far right. You see some problems with, or some interesting use cases of tables that have a lot of tiny rows but not a lot of data, a few huge rows, which is where we get our highest data processing rates. And we're processing, on average 182 terabytes an hour on those job runs, and some poor efficiency data points. And then we can dig in with some other graphs and find out, okay, why did we have poor efficiency? Well, it was slow materialized time, which is a way of us saying the slowness was due to us spending too much time writing back to S3. You can find other data points that are pointing to high overhead, where you're doing other things besides the actual work on your cluster, and some slow cluster setup times as you're getting into the larger clusters. And to show that, with our smaller clusters, less than 10,000 CPUs, you have less than 20% overhead provisioning EC2 instances, but then that goes up to 30 to 50% overhead provisioning EC2 instances above 10,000 CPUs. Going back to benefits of using something like Glue if you don't have huge data volumes. And again, you see here the 60% materialized time in that regressive data set we saw earlier going to S3 writes. And then smaller clusters generally have less overhead overall. Larger clusters, 40 to 70% overhead overall, greater than 10,000 CPUs. And this overhead, if we break it apart, the overhead from just the tasks, like scheduling tasks and cleaning them up, and the RAID driver grows larger the larger the cluster gets as well, compared to just provisioning time, which dominates on smaller clusters. And also, cluster sizing is hard. This graph just shows we're not very good at utilizing all of our object store memory. We need to get better at tuning and choosing the memory sizes that we have on our clusters. We're overly cautious right now. We don't use enough. And so in conclusion here, if you're thinking, should you start migrating all your Spark jobs to Ray? I don't think these results are really a green light to say, all right, you all rush out and start migrating all your Spark jobs to Ray, because there's no paved road to translate them all from Spark to Ray. Spark's still more general and feature-rich for data processing than Ray. And if you just run your existing Spark jobs on something like RayDP, you shouldn't expect comparable improvements here, right? So if you want to have some key takeaways, I would say the flexibility of Ray Core is what we've illustrated here, lets you craft optimal solutions to very specific problems. And we've given an example of a very specific problem we've crafted a more optimal solution for with Ray here. And the ExoShuffle paper is an interesting use case where you can see more general examples of how Ray can improve the data processing space in general, and has by setting the 100 terabyte cloud sort cost record with $97. So in conclusion, I think Ray has the potential to be a world-class big data processing framework, but realizing that potential takes a lot of work today. And very quickly, some future work we're going to do. I want to call out the daft project to you guys if you haven't heard of it. That's its link there on GitHub. It provides fast, scalable Pythonic data frames that can run on Ray and convert to and from Ray data sets. Right now we're working with it. As you saw earlier, we had that materialize regression. That's all writing to S3. Reading and writing from S3 are key bottlenecks for our workflow, for tons of workflows, file I/O in general. We're working on solving that problem first with daft. Our long-term goal with daft is to convert our whole compactor from thousands of lines of code down to a few elegant lines of daft data frame code without sacrificing efficiency, scalability, or reliability. And we're doing ongoing tests with it in production right now. And some S3 benchmarks are pretty interesting with it. Basically, you're getting, for single column reads, more than 200% improvement median versus PyArrow, over 1,000% versus S3FS. For single column Parquet reads that we're doing with our production data with daft. And with all columns, you're still getting 23% improvement versus PyArrow and over 400% versus S3FS. And some future work that we're looking to do is bring this Apache Iceberg compaction over to AWS Glue using the DeltaCat project, so you can all use it to do merge on read, copy on write operations in your Iceberg catalogs as well, and benefit from these same efficiency improvements that we've demonstrated here. So thank you all. If you want to reach out to me, I'll be here after this talk, but also ping me on the Ray Community Slack or visit us at the DeltaCat project to review what we just talked about at that link.